All right, today we're going to look at how do we find inverse functions graphically. And what we're basically looking for are two functions to be reflections over this line y equals x. Because if graphs are reflections over y equals x, then they're said to be inverses of each other. All right, so let's look at some examples of that. All right, first let's look at y equals 2x plus 4. The first step here is we're going to graph the relation and determine if it's a function. So y equals 2x plus 4, this is just a line with a slope of 2 and a y-intercept of 4. So go ahead and graph that on your own graph. All right, so here we have this line, and we want to determine, is this relation a function? Well, to determine that, we use the vertical line test. So, yeah, it passes the vertical line test. Is it a function? Yeah. All right, now let's, without graphing the inverse, determine if it will be a function. For that, we need to use the horizontal line test. So, will its inverse be a function? Yes, because it passes the horizontal line test. It never hits the graph more than once. All right, now let's write the equation of the inverse and graph it. So, to write the equation, we swap x and y and solve for y. X minus 4 equals 2y. X over 2 minus 4 over 2 is 2 equals y. All right, now we'll graph that. This has a slope of 1/2 and a y-intercept of -2. All right, so here's the graph of that with the y-intercept of -2, up 1 over 2 each time for the slope. And if you notice, if we graph the line y equals x, which goes right through the origin, right through the diagonals, these two graphs are reflections over that line. So that's how we know that we found two inverses of each other. Another way that we can find inverses graphically is using tables. So here we have y equals x squared plus 1. And the very first thing I'm going to do is make a table from -2 to 2. And to fill in these y coordinates, all I have to do is plug these x's into this function right here. You could also remember that this is just the parent function shifted up 1. So we have the points 5, 2, 1, 2, 5. And go ahead and plot those on the graph. All right, so is this relation a function? Yeah, it passes the vertical line test. But will the inverse be a function? We use the horizontal line test, and we see that it does not pass the horizontal line test. So the answer to this is no. All right, so let's actually figure out for the inverse of this function, what would its table look like? Well, to find an inverse, you just swap x and y. So we're just going to swap x and y in these tables. The inverse function would have x's of 5, 2, 1, 2, 5. And the y values would be -2, -1, 0, 1, 2. All right, now go ahead and plot those coordinates on this graph. And so now graphically, it's easy to see that this is not a function. This input of 5 has multiple outputs along with the 2 and so on. But they still are reflections over the line y equals x of each other. So now let's go back to algebraically and try to write the inverse of this function, just to further show that the inverse will not be a function. So to find the inverse, we swap x and y. So x equals y squared plus 1. X minus 1 equals y squared. And whenever we take the square root, remember that we have to use plus or minus because it's an equation. So y equals plus or minus the square root of x minus 1. Now this should make sense graphically because here we have a square root function shifted right 1, but we have the positive and the negative, so we have the reflection of it as well. Here's the positive of that square root function shifted right 1, and here's the negative. But whenever we combine these two, it's no longer a function. All right, and that's finding the inverse graphically. Goodbye.